This video is on an introduction to sampling distributions. This entire chapter 7 is on sampling distributions. This first video is just a quick intro to make sure that you understand the basics of it all. Alright, so here we go. First off, to understand sampling distributions, we need to understand questions like this. What does the average American earn per year? What proportion of Americans have blonde hair? Well, the first thing we have to understand is that to get these two questions, we would need to sample everybody, literally the entire population. Well, that's pretty hard to do. So what do we do to find the average American earns per year? Maybe we take a sample of 100 people, we ask how much they make, and we get a sample average of maybe something like $54,952 per year. Now, we hope that this sample statistic somehow represents what the population is, but we never know. Another question we could ask is, what proportion of Americans have blonde hair? Well, maybe again we ask 100 people, and of those 100 people, 34 have blonde hair. Therefore, our sample proportion is 34 out of 100, or 34%. The idea is, in both of these situations, this first situation deals with a mean. The second situation deals with a proportion. I'll just say PROP for proportion. Is both of these numbers are samples, right? We don't know if this is necessarily going to be true for everybody. But the idea of statistics, right, the heart of statistics is that it kind of should be, right? We hope that this sample average does reflect what's true for the population. We hope that this sample proportion does reflect what is true for the population. That's the idea here to get us started. So the first thing we have to do is we have to understand the difference between what we call a parameter and a statistic. Now, to understand this, remember that a parameter comes from the population. Okay, easy way to remember this is a P for population, P for parameter. A statistic comes from a sample, and we really need to make sure that we understand the difference between these things. By the way, this is easy to remember because statistic starts with S, and so does sample. Now, there's only two types of parameters out there. The first type of parameter is a mean, right? The mean of a parameter is known as mu. That's the true mean of that population, right? The true average amount of money the average American makes. To get that value, I would have to ask every single American how much money they make and get an average, right? The other type of parameter is a proportion. A parameter, a population parameter for proportion is a P. So this would be the true proportion of people that have blonde hair. And again, to find that, I would have to analyze every single American and find out how many have blonde hair, divide it by all the Americans there are to get that true proportion. Now, for statistics, we also have a mean, but we use a different symbol to represent the mean of a sample. That's X bar. X bar is the mean of a sample. And same thing for a proportion. If we have a proportion that came from a sample, to represent it, we do use a P, but we use a P up here as well. So to make a difference, we put a little P hat on it. So a P with a little hat, just a little kind of a X, or not an X, but like a little hat, a little raised to symbol above it. That symbol represents that it's a sample proportion, not a true proportion from a population. So we're always going to work with either means or proportions. Okay, so we have means, mu, proportion P. When we're working with statistics, the mean is the X bar, the proportion is P hat, P with a little hat on it. Okay, so what is sampling variability? Well, sampling variability is pretty important to understand, and this is the idea that every sample I take might be a little bit different, right? In that first example, we looked at 100 Americans, and we got a sample of $54,952. I think that was what I said. Now, imagine if we took another sample of a different 100 people, right? A different 100 people. We are probably, in fact, pretty much guaranteed to get a different average. It might be something like 54,846, or maybe we do a different 100 people and we get a sample average of 50,810. Again, the idea is we can go on and on. Samples vary. So from one sample to another, to another, to another, to another, we're going to have some variability. This is the idea of sampling variability. Same thing holds true if I sample 100 people and I ask how many of them have blonde hair. I might get a sample proportion of 34%, but I might ask another sample of 100 people, and this time I might get a sample of 40%. I might ask another 100 people, and this time I might get a sample proportion of, say, 28%. The idea that sample to sample to sample to sample varies is this idea of sampling variability. In fact, that's the one thing that's kind of true in this world, is that samples are going to vary. And the whole idea is if we understand how samples vary, we could start to pin down what the true population value would be. All right, so to illustrate this idea of sampling variability, let's look at this issue right here, this situation. Imagine a bag of 200 poker chips, 100 red and 100 blue. The population parameter proportion of red chips is 0.5. So this means that P, not capital P, just P with no hat, is 0.5. The population of the entire bag is 50% of chips are red. But if we take out random samples of size 20, we might not always get 50% red chips. And this chart down here tries to show that. For example, sometimes we might open up a bag or we might pull out 20 chips and 15 of them are red. So that's 75%. 15 out of 20 is 75%. So that would be, right here at 75%. Sorry, ignore that first dot. Or sometimes we might open the bag up and there's 12. 12 out of 20 is 60%. So that would be a dot right here under 60%. Sometimes we might open up the bag and we pull out 20 chips and only 8 of them are red. 8 out of 20 is 40%. So that would go right here. The idea is that these dots represent a bunch of p-hats. And sample statistics like p-hat, like x-bar, they're going to vary. They're not always going to be what's true. Yes, some samples might be the 50% that's true, but you might also get some samples that are way far away, or some samples that are close to 50%, but not exactly. This is exactly what we're talking about when we reference sampling variability. The idea that samples, p-hat, right, all these dots represent p-hat after p-hat after p-hat. Pull out a sample of 20 chips, pull out a sample of 20 chips, and I'm going to get different proportions every single time. Now, the good news is they should all be close to 50% because, remember, that is what's true, but that doesn't mean it's always going to happen because things vary. Now, this brings us to the definition of what this entire video is about, sampling distribution. This is a pretty important definition, so make sure you take the time to pause, write it down, whatever you got to do. The sampling distribution of a statistic is the distribution of values that taken by the statistic in all possible samples of the same size from the same population. So a sampling distribution is just a picture of what all possible samples of size n would look like. Again, it has to represent all possible samples of size n taken from that population. So go back to real quick right here. This picture I'm trying to draw for you is a sampling distribution, but it doesn't represent all samples because I got to pick out every possible sample of size 20 from that bag. And as I do that, I'm going to start to have dots all over the place. Sometimes I'll get 40% red, sometimes I'll get 60%, sometimes I'll get 70, sometimes I'll get 35, sometimes I'll get 25, sometimes I'll get 55, sometimes I might get an 80, 75, a 70, another 50, sometimes 45, sometimes. Again, as I start to analyze what every possible sample of size 20 would look like, that picture turns into what we call a sampling distribution. So, in a nutshell, a sampling distribution is what all possible samples would look like. Okay, what the statistic from all possible samples would look like. That last example we did dealt with proportions. Let's do a quick example that deals with means. So, imagine a bag of 500 random numbers. The population parameter would be the average of all 500 numbers. So what I'm going to do is I'm going to tell you that I took out all 500 numbers, I add them together and divide by 500, and the average was 75.26. Okay. Now imagine that I take out a sample of size 30. Right? This is going to be a sample of size 30, a sample, x bar. There's only 30 numbers, right? And let's say that the sample of those 30 numbers was 70. Well, I take out another sample, and another sample had an average of 69.2. Another sample of 30 had an average of 75.8. Another sample of size 30 had an average of 84. Another sample of size 30 had an average of 73. Another sample of size 30 had an average of 72.4. You get the idea. So what's a sampling distribution? Well, it's a picture of what every possible sample of size 30 would look like. So I'd have to create a straight line here. I'd have to start kind of putting some values on here. So here's 70, here's 75, here's 80, here's 85, and I start to lay out what happens. For example, the 70 would go right here, the 69.2 would go right before it, the 75.8 would go over here somewhere, and I would start to build a model of what every possible sample would look like. Now, I only did a couple samples here. You have to understand that a sampling distribution shows you what every possible sample would look like. So you'd start to see some values average around 75, a couple 80s, some might over here, some might here, some right here. You might get a really low average every now and then. But again, as you start to look at the results of every possible sample, you start to build what we call the sampling distribution. The idea that you're not always going to get the same value is the simple idea of sampling variability. Samples are going to vary. But when you look at a picture of all samples, you start to notice that things pile up. All right, now, the other important topic of this video is that you need to be able to understand that there are three types of distributions. Okay? Now, we're going to go back to our poker chip problem to really understand the different types. The three different types of distributions are: 1, a population distribution. That's what the entire population looks like. 2, a single samples distribution. That's what one sample looks like. And 3, a sampling distribution, which we're trying to focus on. So I need you to understand that these are all very different things, and that's why you're going to understand why this last one is really important for the future of this class. So for example, right here, this first one is a population distribution, right? Well, if we have 200 total poker chips, we know that 100 of them are going to be blue and 100 of them are going to be red. That's 50% blue, 50% red. This is exactly perfect, right? This is what we know from the entire capital N 200 chips, right? That's it. Pretty simple. 100 blue, 100 red. That's what the population looks like. We know that for a fact. Now, these two in the middle here, these are examples of a samples distribution, just one sample. For example, this particular sample right here had 8 red. So of the 20 chips we pulled out, remember this was a sample of 20 chips, of the 20 chips, 8 were red. That means 12 were blue. So this is a very basic graph. Just shows 8 red, 12 blue. That shows that 40% of the chips were red. Very, very simple. 60% would be blue. Here's just another one, because remember, samples vary. So here's another one where we had 11 red chips. That would be 9 blue chips, because we had 20 chips as well. And again, that's a sample proportion of 55%. 11 out of 20, 55% red, 45% blue. Now, what's a sampling distribution? Once again, a sampling distribution is what every possible p-hat would look like. Every possible p-hat, right? So, again, these two are just 2. This 40%, this 55%, these are just 2 of every possible sample of size 20. So that 40% would be one of these dots. And again, these dots don't even look like dots because there's so many of them, but they're all crunched together there if you zoom in. And then the 55% would be one of these many dots here, but you have to understand that a sampling distribution doesn't just show a couple samples, it shows every possible sample of that size, in this case size 20. So it shows what every possible sample of that particular size would look like. Alright, now the last thing we want to talk about in this video is describing a sampling distribution. When you look at a sampling distribution, when you see a sampling distribution, there's 2 important things you want to talk about. The first thing you want to talk about is the center. Now, the center is going to be where the dots pile up around. So, for example, the last couple of examples we've seen, we kind of saw the dots start to pile up, and we saw them pile up in the center there. Well, that center right there is the center, right? And this is actually really important. If it's truly an unbiased estimator, if we truly took random samples out, the center of your sampling distribution should be the true value. Pretty cool, right? Go back to here. If this truly shows what every possible sample looks like, notice smack dab in the middle is the truth of 50%. So that is really, really important, right? So imagine if we were trying to find the proportion of people that have blonde hair, and we started to look at samples, right? And we had 30% here and 40% here, and some samples were low, some samples were high, but we start to see that it piled up around here, right? Most samples piled up around here, then we can make a pretty smart, intelligent guess that the truth is about 35% of people have blonde hair. So the center of a sampling distribution should start to pile up around the truth. Pretty cool. But we also have to understand that not all samples are the same. There is a variability of a statistic, right? This is the idea of sampling variability, right? Some samples are going to be a little bit higher. Some samples are going to be a little bit lower in all these cases. That's the idea, is not every sample is going to be exactly what the truth is. So how samples vary is going to be an important topic for us to talk about. But one important thing I want you to at least learn in this video is that your sample size matters, right? If n is bigger, you will have less variability. Variability. Sorry, kind of spelled that wrong. The idea is that if you take a bigger sample out, you will have less variability, right? This makes complete sense because, yes, you have these couple low values on the end, but when you take out 20 chips, it's pretty easy that you could end up with, maybe only 2 red chips, and 2 out of 20 would only be 10%. That could happen. It might happen every now and then. But if I take out 50 chips, 70 chips, 80 chips, I should have that be less likely to occur. So when you have a bigger sample size, your sampling distribution will vary less. It will be more narrow. It will be more centered to the truth, right? Go back to the very, very, very first question that we asked. I'll kind of scroll to it here in a second. And that is, what does the average American earn per year? Well, if I only ask 3 people, I could get a number that's extremely high or extremely low. I could get a number that's way far off from the true mu. But if I ask a sample of, say, 3,000 people, in that sample of 3,000, I might have some wealthy people, I might have some more impoverished people, and then the average kind of gets closer to what's true because I have a larger sample that better reflects the population. And if your sample is bigger, hence better representing the population, you're more likely to get a truthful answer. Now, your samples are still going to vary, right? But you're more likely to get a more accurate answer. So that's a quick video. Again, not too long. Hopefully you didn't think so. But it does give the quick, important ideas that you need to have for Chapter 7 over sampling distributions. All right, thanks a lot for paying attention. In class, we'll do some exercises and some activities. Hopefully it all makes sense.